In this presentation, we are going to be looking at the negative binomial distribution and how the negative binomial distribution can be used to model a Poisson-gamma mixture. We're going to be using the method of moments in this analysis, so let's just bear with me there for a second. Suppose that the number of accidents per year per driver in a large group of insured drivers follows a Poisson distribution with mean lambda. So just as a quick remark, the mean lambda here is a random variable as opposed to a constant. And the random variable is distributed according to the gamma distribution, okay? So hence the name gamma, Poisson-gamma mixture. And we have a mean of 0.6 and a variance of 0.24. Okay, determine the probability that a randomly selected driver from this group will have no more than 2 accidents per year. So that's a straightforward enough question there. No more than 2, okay? So that means 0, 1, or 2, and get the so that's it. So first off, here's the method of moments. Now this is for the gamma distribution. I should have been a bit more specific about that this is the method of moments for the gamma distribution because that's what we're told. Just be careful about that because the gamma distribution, first off, it's not the negative binomial distribution we're using the method of moments for, it's the gamma distribution. Also, just actually remark upon the shape of it. So the mean here is parameterized or is calculated using alpha times theta, and the variance is alpha times theta squared. Now I sort of picked this approach really because of simplicity, but there are other approaches about how to do it. Essentially, just as a remark, I'm parameterizing the gamma distribution in terms of alpha and theta, and that is the shape parameter and the scale parameter. Okay, just so you might see it there at the bottom of the screen. Okay, so there are other ways of specifying the gamma distribution, for example, using the alpha and beta, where beta is the rate parameter. Okay. So setting alpha theta equals 0.6 and alpha theta squared equals 0.24 essentially should be straightforward enough. We should get alpha equals 1.5 and theta equals 0.40. So it's probably a good idea just to actually sort of make a quick statement here. The parameter alpha follows a gamma distribution with shape parameter alpha equals 1.5 and scale parameter theta equals 0.40. Just a very explicit statement of what the gamma distribution, how it's distributed and what it's doing. Okay, so the Poisson-gamma mixture follows a negative binomial distribution, hence the whole point of the exercise, and the rate parameter is based on the parameters. The parameters of the negative binomial distribution is based on those parameters. So essentially, we let R, which is the negative binomial parameter, that takes the value of whatever alpha is, and P takes the value of 1 divided by 1 plus theta. Okay, 1 divided by 1 plus 0.4, which is 5 over 7. Now, just actually as a quick remark, care must be taken here. Be careful around when you're doing these sort of things. The reason is that there are multiple specifications of the gamma distribution, there are multiple specifications of the negative binomial distribution. There's one that sort of fits fairly well, okay? But just remember that they sort of match up, okay? So just in case you're running into trouble, just take care to see if you're using the correct specification in each case. Now, I don't really have time to do that, but just actually check your tables and so on and practice this a bit and get familiar with all the various types of specification. Okay, so I'm going to continue on. The PDF of the negative binomial distribution, here is the binomial coefficient, okay? This is the particular format of the negative binomial distribution I'm going to use in this instance. The binomial coefficient of k plus r minus 1, k. Okay, so from k plus 1 minus r, choose k. P to the power of r times 1 minus p to the power of k. Okay, now p to the power of r, this term here is going to appear a lot. So this one here, sorry, I shouldn't have erase that, but so it's going to be consistent the whole way through. So I'm going to treat this as a coefficient. 5 over 7 to the power of 1.5, that gives us 0.6037. So we'll make a little note of that there, and we'll just sort of come back to that later on. Okay, that we'll sort of see that number there pop up again and again. So now we can use our expression to calculate the individual probabilities that we're going to need. First off, what we're going to do is calculate the probability of x equal to 0. Now, the binomial coefficient is from 0.5, choose 0. Okay, just actually let's go back up there. Here, k is equal to 0 and r is equal to 1.5. R minus 1 means plus 0.5. Okay, so 0 plus 0.5, from that choose 0. So 0.5 choose 0, that's just 1. Okay, so that's always the way with binomial coefficients, that if the bottom term is 0, that means the binomial coefficient is 1. The last term, 1 minus p to the power of 0, is 2 over 7 to the power of 0, and that's 1 over 1.4, or the complement of that, and that's anything to the power of 0 is 1. So the probability of x equals 0 equals 1 times 0.6037 times 1, and that is 0.6037. So that again was p to the power of r. Okay, so the next one, probability of x equal to 1. From 1.5 choose 1. That's simply 1.5. Okay, 1 minus p to the power of 1, 2 over 5 to the power of 1, that is 0.2857. So put it all together. Remember, this term is constant, p to the power of r. 1.5 times 0.6037 times 0.2857, that should work out to be 0.52587. Just as a remark, it just looks like these numbers are the same, but actually they're different numbers. Very close, but different. Okay, so just watch out for that. That isn't a typo, you're just looking at two different numbers. And finally, the probability of x equal to 2, that is equal to, first off, the first term here, from 2.5 choose 2. So this is probably a good example of working with these binomial coefficients. So we look at the number below and get on the bottom part, and get the factorial of that, 2 times 1. Okay, and then we have the factorial for the number above, so to speak, that works on the basis that it has the same number of values, the same number of components as the term below. So 2.5 times 1.5. Working that out, we get 1.875. 1 minus p squared is 2 over 7 squared. That is 0.0816. So piece them all together. Again, we have 0.6037 p to the power of r there. Up above, we have 1.875. And here we have 0.0816. Put that all together, and we get 0.09236. Okay, I'm just going a bit excessive with the number of decimal places, just so you can check how close you get. Okay, so the question asks us, find the probability that x is less than or equal to 2. Essentially, add up all of those numbers together. Okay, our three calculations, and we get 0.9548. That's the answer we're looking for. Now, in this case, what I've done here is I have checked this with the R programming language. Okay, so here R is equal to 1.5. That's my R value, and P is 5 over 7. Okay, so R and P there. So that's the R programming language. D binom, this is the probability mass function of the negative binomial distribution for each of these values, 0, 1, and 2. Just in case you're going to employ that as well. So I sort of actually did this just to check my own answers. And also just actually a remark upon the fact with the multiple specifications of the negative binomial distribution, this is the one that our programming language favors. Okay, the approach I've used here in this presentation. Okay, we'll leave it there.